Welcome back. Today's lecture is going to be a bit of a smorgasbord of a couple of topics related to orthogonality. Four of them in particular, all related, but each a little separate unit. So I'm going to start by talking a little bit more about the QR decomposition. And what I want to explain is one of the reasons that this is useful. I mean, who cares? You can write a matrix in the form QR. What's the big deal? So remember, the QR decomposition says that if you have an invertible matrix A, you can write it uniquely as QR, where Q is orthogonal, meaning QQ transpose is the identity, and R is upper triangular with positive entries on the diagonal. And I want to talk first a little bit more about these orthogonal matrices. I've talked about this before, but some of this bears repeating. So matrix is orthogonal and if and only if it has the following property: it preserves length. That is to say, if you have a vector v and then you apply q to it, the result still has the same length. So this is a fact. This is not the original definition, which had to do with the rows being orthonormal, but it's a fact that it's the same as preserving lengths. And it turns out that it's also the same as saying that it preserves angles, which is to say inner products, which is that if you have two vectors v and w, then the inner product of v and w is the same as the inner product of qv and qw. So one way to think of this is to say that q is a rigid motion of the plane. And let me illustrate what I mean by that. So for example, in R2, what's an orthogonal transformation? Well, look at the circle. The circle consists of the vectors of length 1. And how can you have a linear transformation which preserves lengths? That means it has to take the circle to itself. And it's rigid, it preserves angles. What can it do? Well, basically it has to be a rotation by some angle theta. That's something you can do. Well, that's not quite everything. Oh, well, hang on. So the way you write a rotation is as a matrix cosine, sine, minus sine, cosine. But another thing you can do is reflection, which is to say you can take your circle and you can draw a line through the origin, and you can reflect the entire plane through that line. And if you do that, it takes the circle to itself. The circle is symmetric. It's got mirror symmetry. And that's another example of an orthogonal transformation. And it's not so hard to see that that's all of them. In the for the 2 by 2 case, it's a fact that if you have a 2 by 2 orthogonal matrix, either it's of the form cosine, sine, minus sine, cosine, in which case it's rotation, or it's of the form cosine minus sine, and then you just change the signs, excuse me for the pun, on the column on the right to make it like this. So this first guy here, you notice it has determinant 1, cosine squared plus sine squared is equal to 1, and this is a rotation. This guy here has determinant minus 1, because when you take the determinant, you get minus cosine squared minus sine squared, which is minus 1, and that's a reflection. And every orthogonal transformation of the plane, every 2 by 2 orthogonal matrix is one of these. So in a way, these are very easy to understand. They're simply rotations and reflections. So let's think about this upper triangular matrix. In the 2 by 2 case, it looks like this. And remember, I'm saying that A and C are positive. So for example, if you take a diagonal matrix, the way I like to think of this is it's just dilation in the two coordinates. You're scaling x by A, and you're scaling y by C. And again, that's something that's very easy to understand. It's easy to draw a picture of what this is doing. So let's say you scale by, I changed to be a in the x factor and b in the y. So that says you're just stretching by a factor of a in this direction, and you're stretching by a factor of b in this direction. Possibly different, but anyway, that's a fairly elementary operation. And you're just stretching by possibly different amount in the two directions. And one last thing to look at is a matrix like this. Suppose you had something like this. What does this do? This takes xy to what? To x plus by y. And if I write that as xy plus, y times b0, you see that what is this doing? It's taking your vector xy and it's adding some vector in the x direction to it, this b0 guy. And how much you're adding depends on y, so this is called a shear. It's sliding everything from right to left, and you get more and more sliding as you get away from the x-axis. So that's not quite as elementary as the previous two, but also not hard to understand. And the conclusion of all of this is that if you use the QR decomposition to write A is equal to QR, where A is invertible, it says that any invertible matrix, any invertible linear transformation can be viewed as a composition of some very basic ones. That is to say, the way this matrix moves vectors around, you can break it into a bunch of steps. You can do a rotation composed with a reflection. Possibly there might also be a stretching in it, and there might be a stretching or dilation, and there might be a shear, and those four together give you any invertible linear transformation. So this gives you a way of understanding any invertible matrix. And for example, if it's sometimes you think of a matrix as being all Q or all R. If it's all Q, it's just rotations. If it's R, it's dilations and shears. And it really helps to understand the general matrix by breaking it down this way. It gives some sort of order in the universe of all matrices. And we'll come back to this later and do a couple of more concrete applications of this. But for now, I just want to say that it gives you a sort of geometric way of thinking of any invertible matrix. Okay, I next want to talk just very briefly about something called Legendre polynomials. This is really a very pretty subject, and you may have seen these somewhere, or you may yet someday see these somewhere in an application, and it's quite a elementary thing, so let me just go over it briefly. The point here is to look at the space of polynomials a0 plus a1t plus a2t squared and so on, polynomials in a variable t, and this is a vector space. We've talked about this, and I'm just going to consider these as functions of t between -1 and 1, and put the usual L2 inner product on this space, which is to say the inner product of two polynomials is the integral of f of t and g of t dt from -1 to 1. And remember, that says that the length of a polynomial is the integral of the absolute value of f of t squared dt, and the square root of that. So this is a standard inner product on the space of functions. And for example, let's just sort of get the idea here. Take the function 1, the constant function 1. What is its inner product with itself? Well, by definition, that's the integral from -1 to 1 of 1. And you all remember your calculus, right? That turns out to be 2. And similarly, if you take the inner product of 1 and t, what do you get? You get the integral of t dt from -1 to 1, and that's 1/2 t squared, and that's 1/2, 1 minus 1, which is 0. So that says with this inner product, 1 and t are orthogonal to each other. So that's kind of nice. So wouldn't it be nice if 1 and t squared and t cubed and so on, if all of those polynomials were orthogonal? So let's check. 1 and t squared is the integral of t squared from -1 to 1. And that's 1/3 t cubed, and that's, let's see, that's 1/3 1 minus a -1, which is, oh dear, it's 2/3. It's not 0. So 1 and t squared are not orthogonal. Okay, well, if you're Legendre, you say, let's make them orthogonal. Let's apply Gram-Schmidt and make them orthogonal. And what you get is the Legendre polynomials. So it's a very simple idea. You start with the usual basis of polynomials, the powers of t, and you apply Gram-Schmidt to get an orthogonal basis. So I said orthogonal, not orthonormal. We're not going to normalize them, or at least not quite yet. So here's what you get. So the first polynomial you start with is 1, of course. So these are as I said, these are called the Legendre polynomials. And here are the first few of them. For example, there's P0 is equal to 1, and P1 is equal to t, and P2, it starts off with t squared, and then you have to subtract off 1/2. And then P3 starts off with something involving t cubed, and then you have to subtract off something involving t. And P4 starts with some multiple of t to the 4th, which turns out to be this. And you also have to subtract off a t squared and a constant term, and so on. And so what you see is that the label on the polynomial is the degree. P2 is some multiple of t squared, and P3 and P4, so on. It's telling you the top degree. And there is a normalization, which is not the usual one. They're normalized so that these polynomials evaluated at 1 are equal to 1. So that accounts for some of these coefficients. I don't care too much about that. So anyway, the main point is that at the end of this, what you have is a bunch of polynomials, P0, P1, P2, and so on, where pk has degree k, and this is an orthogonal basis of the space of polynomials. And you'll see in a little bit, it's always nice to have an orthogonal basis for applications, and that's what the Legendre polynomials provide for you. And again, they're not orthonormal, they're not length 1, but that doesn't matter so much, and we'll see that it's often very useful to have an orthogonal basis of a vector space. And okay, let's go on. Next, I'm going to talk about orthogonal projection. So let's recall all this business about the closest point and least squares and all of that. So you have a plane W and a vector V, and we're interested in finding the closest point in the plane to V. And the picture is like this. You draw the perpendicular line to the plane, and the closest point is given by what's called the orthogonal projection. I've mentioned this before. I'm going to say it a little more carefully now. P, there's this matrix, this linear transformation, which gives you this projection taking V onto W. And remember that the least squares algorithm tells you what P is. It's this matrix A transpose A inverse times A transpose. That's this matrix which gives you the closest point, where A is the matrix whose columns are a basis of the subspace W. Okay, so that's the least squares method. And I want to discuss a variant of it now. doing it a slightly different way, which takes advantage of some stuff about orthogonality. And the idea is, suppose that this matrix, this basis that we had, V1 through Vm, suppose it's orthogonal, or actually orthonormal. Suppose the basis is orthonormal. Remember, you can always do that using Gram-Schmidt. So it turns out that if you have an orthonormal basis, the formula is much, much simpler. And there's a very easy way to compute the closest point. So that's what I'm going to describe now. So let's write PV as a linear combination of this basis, right? Remember, PV is in the subspace W, so you can write it uniquely as some linear combination of the basis vectors. And I just need to figure out what these AIs are. That's what we need to do. And now here's a nice thing about orthonormal bases. This is a property that's special for orthonormal bases, which is the following. Suppose I have a vector a1 v1 plus dot 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 an vn written in some orthonormal basis, and I want to take the inner product of that with some vj, with one of the vj's from the basis. What is that? Well, let's see. When you take this inner product, all of the terms are 0 except for the jth term, and you get aj. I'm sorry, that's a misprint. I wrote ai. Of course, that's supposed to be aj. So here's the picture. We have this vector v, and we're looking for pv, which makes this orthogonal. So by definition, that means that this vector pv minus v is supposed to be orthogonal to w. So this vector pv minus v had better have inner product 0 with all of these vj's, which are the basis of w. And now we just need to write out this condition. I've written pv as a1 v1 up to am vm. So we take that, and then we subtract v from it, and we take the inner product with vj, and what do we get? Well, we're supposed to get 0. Let's see. Well, by what I just said, when you take this inner product, you pick out the aj term. On the other hand, this vj inner product with v, that's just what it is. You can compute it, so you just get vvj. And there's a formula for aj. This is supposed to equal 0, so I've concluded that aj has to be equal to the inner product of v and vj. So in some sense, you're done. There's no matrices to write down. There's no AA transpose, all of that. You just need to write down these numbers AJ. So let me summarize that. So the picture is the following. This is a new version of the least squares algorithm. And suppose you have a vector V, and we're trying to find the closest point on a subspace W, which is spanned by a bunch of vectors Vi, and I want to make the special assumption that the Vi's are an orthonormal basis of W. Then the closest point has a very simple formula. The closest point to V in W is A1 V1 plus dot 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 up to AM VM. And the simple formula is AJ is simply the inner product of V and VJ. You're given V, you're given this basis VJ, you compute this number, and then you're done. And this is for J running from 1 to M. Okay, so the idea here is that there is some extra work in computing this orthonormal basis. You have to do Gram-Schmidt. That's a little bit of work, but the payoff is that once you've put in this extra work, then computing the closest point to anything is extremely easy. And it's one of these things where you do a bunch of work up ahead once, and then the projection of any vector is elementary. Okay. Now here's a variant of our variant, just a slight one. Suppose we have this W, and it's a span of a bunch of vectors v1 through vm. And let's say that they're orthogonal, but not necessarily orthonormal. And remember, when we run Gram-Schmidt, it's often nice to get an orthogonal basis and not worry about normalizing it. Well, this works just as well. Then the formula for the closest point, the projection of a vector, is a1 v1 up to dot 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 am vm. And ai is now given by the formula v inner product with, aj is the inner product of v with vj, and you just need this normalization term divided by the length of vj squared, vj in the denominator. So in the case of an orthonormal basis, the denominator is 1, but in general you just need to put that there, and that's just almost as easy as the orthonormal case. All right, for my last trick, I'm going to talk about orthogonal complements. So we have a vector space V with an inner product, and of course you're welcome to think that V is Rn, and the inner product is the usual one, but that doesn't really matter here. And suppose we have a subspace of V called, let's say, W. We define W perp, this little symbol here is pronounced perp, or perpendicular, or orthogonal complement. The orthogonal complement of W is the set of vectors which are orthogonal to every vector in W. So let's just draw the basic picture here. We have a subspace W like this. What are the vectors which are orthogonal to it? Well, they're just these guys here, the line which makes a right angle with W. So here's W perp. And it's quite easy to see that the orthogonal complement of a subspace is a subspace. Here's the result. So you have this vector space V and a subspace W, and this W perp. Then, first of all, W perp is a subspace, and the summation of the dimensions add up to the dimension of V. And sometimes we say that these are complementary subspaces because their dimensions add up. And there's also a sort of stronger property, which is that any vector in V can be written as a sum of a vector in W and a vector in W perp, actually uniquely. So W is in W and W prime is in W perp. And this is a unique decomposition. And let me just illustrate this with a picture. Here's W and W perp. And if you have any vector, well, you can write it as a vector in W. I'll draw it in red. And a blue vector in W perp. That is to say, the picture looks like this. Okay, this is fairly easy to prove. I'm not going to prove it. I'm just going to illustrate it with a very basic example, which in some sense is a proof practically. But anyway, let's just look at this key example, which should help you think about it. Let's take V to be Rn with the usual dot product, and take W to be this Rk, where you, on the first k coordinates. So I'm going to call this Rk, even though I don't really like to do that. It's what it really is a k-dimensional subspace, but anyway, it's this Rk sitting like this. And then W perp, what is W perp? Well, something's going to be perpendicular to this. All of these guys, the first k vectors had better be 0, but then the remaining ones can be whatever you want. So this W perp is a little copy of RL sitting in the last coordinates. And here k plus L is equal to n. And so you see that any vector, A1, let me write it as C1 up to Cn, any vector can be written as, well, you just pick out the first k coordinates and then put in some zeros, and then you add that to a bunch of zeros and then the remaining coordinates, and you've written this vector as this vector in W plus another vector in W perp, and you see that the dimensions add up as I said.